Thank you very much, Dr. Anne-Christine, for that lovely introduction. Hello, everybody. It's a great privilege to be able to present what is essentially a research project which is starting to show its flowers, because I absolutely love that expression. Thank you very much. I've learned some wonderful things throughout the day. Bread and roses. I think we could qualify what I'm going to show you as roses. But I think if my presentation can be pulled up on the screen, that would be good. I'm seeing you and Christine right now. I think I should be seeing my presentation. Oops.
Your presentation is there already.
It is there. Okay.
Yes.
Okay, I can only see it on the little screen. Okay, well, it's going to be a little bit difficult for me to follow, but I'm going to try and go through it. Yes, ArtBuild, we're a practice, architectural practice. We've been around for 30 years. We have offices in Paris, Brussels, and Luxembourg. I'm going to be taking you through where this research project came from, and then explaining to you a little bit what we're intending to do for this summer, this temporary amphitheatre, which will be erected on the Grand Palais in the Grand Palais Éphémère in Paris. Okay, so yeah, the life expectancy of office buildings, we were early adopters with timber, and we decided that there was certainly some space to be done with mass timber in office buildings. But, you know, the industry, when you talk to people, whether it's developers, investors, contractors, most people come to the conclusion that office buildings will pretty much be obsolete or redundant in 30 years' time, which is really shocking. Even though we can try and build in reversibility and evolutivity, it's actually 30 years is pretty much a standard now. So people are starting to see buildings that they've built at the beginning of their careers deconstructed now. So we're coming face to face with this reality. And it was when we handed over this project, which is one of the first mass timber office buildings in the world. I think it was 2017, 6,000 square meters on the outskirts of Paris. When we handed this building over, we were aware that there were lots and lots of criteria which would be applied as a benchmark to this building, which we weren't comfortable with. The idea of taking this building apart and having to burn all of the wood in order to get the full life cycle analysis didn't make any sense. We thought we've got to do something to be able to recycle, to upcycle, to do something with these wonderful building elements, which make up part of what we now do when we start doing big mass timber buildings. And this was the mission statement we came up when we wanted to do this research. We called the research project MUSA, and the idea was really to take CLT panels, which are now the industry standard for big mass timber buildings, to take these CLT panels, to transform them somehow using parametric tools, using CNC, using robots, and see if we could do something to keep these panels intact, but to make something even more beautiful than the simple sort of stacked like, you know, you stack cards up and you make buildings in a very, very sort of basic way right now with CLT, but we could do something and free our minds a little bit, get back to that roses creativity thing, using these parametric tools. So I met a young student who was just doing her degree in architecture, who introduced me to the lattice, hinge, and kerfing. These are traditional techniques which instrument makers, musical instrument makers use to transform timber or transform wood and to make them into completely different shapes. And we thought we can upscale this, but we can upscale this not for decorative elements, but for mass timber elements. So we can do this with CLT panels, or we thought at least we can try. When you look at these elements very closely, you realize that there is actually a particular calculation, engineering calculation, to be done on each one of those torsion modules of wood. If you can find the right parametric calculation to do, you can apply that to different types of wood and different scales of CLT panels. And that's what we started to do. We started to find out where we could find the tools to do this with CLT panels. So this is not plywood and small woods. These are big CLT panels. These are floor slabs and load-bearing structures. That was quite successful. We began to find that there was a nice balance between 6 centimeter thick panels and the parametric tunings. We did our first experiment, which was in fact the welcome structure in this building, which you saw, which was handed over in 2017. But we thought, okay, now get this bigger, get this scaled up. To look at structural systems, what can we do once we've got that curved CLT panels? We went back to nature and we found a double wall structure. We started to work with, rather than a simple load-bearing element, we started to combine these 6 centimeter panels, and with the precision of our numerical tools and our calculations, we started to make these walls, which, being cut in a particular way, according to this parametric tool, could make us some wonderful, wonderful load-bearing elements with an awful lot of freedom from a plastic point of view of what we can actually do to make things which are totally, totally different. Hollow cavity, so you can carry fluids, you can put insulation in, you can put thermal inertia, and we came up with a whole new constructive system, or at least we thought. Then we were looking for opportunities to what to do next with this structure, how to then take this beyond. And I'm afraid I can't see, this is such a small thing on my screen, and I can't even read what that is on the slide. So somebody could please pull up the screen, that would be really helpful. There we go, thank you. That's wonderful. That's great. Okay, so this is just a recap. What's interesting in this lattice hinge kerfing approach? This is reversible bending. So basically, you're taking your elements, you're slicing them up, you can flat pack them again. That makes for flat, efficient transportation. The digital tools give you an incredible engineering flexibility in terms of what you can do and how you can recompose these elements and put them together again. Custom bending, that means you can pretty much design them to any shape that you want. There is this upcycling, so we're back to this kind of some of these words that we heard together today, the cascade, which I also think is a lovely, lovely term. And then you've got the acoustic, biophilic, and aesthetic qualities of timber. So you're combining a bunch of things, qualities of timber all together, and you're addressing this problem of reducing the redundancy of the buildings. We were then commissioned to design a welcome pavilion for the agricultural fair in Belgium, in the Wallon region of Belgium. And we thought, well, let's use the CLT bending process. And we started to think, well, what in nature can we be inspired by in order to come up with a constructive system which is going to give us that the particular form or the particular use that we're looking for? We looked at slow growth patterns. I was a biologist before I was an architect, so that kind of explains why we keep going back to these funny nature models. But that's bone to the left, and those are banana trunks to the right. Banana trunks grow incredibly fast, bone grows incredibly slow. We looked at the fast growing because we thought there must be something interesting in that fast growing model, which gives us a very, very high ratio of structural efficiency compared to the actual matter that you're putting into it. So as we look closer at the section through the banana, we begin to understand how the whole thing works together. We start modeling that up using our CLT 6 centimeter panels, and how we're going to cut them in order to form those concentric spirals. We start doing our first models, our first real wooden models. And then that's the thing once it's built. So obviously I'm jumping through some steps very, very fast, but that was the welcome pavilion in its final state. That's Sasha. She is our parametric priestess. She's the one who did all the coding for this. And you can see her soaking up the biophilic elements of the wood. I also heard this wonderful term, acoustics, the helmet resonator. I think this is one big helmet resonator that we built here. But it was just magnificent, because this is when architecture comes back and tells you how beautiful, simple things can be. These basic construction elements, CLT, this is unsanded CLT. It's just been cut with a circular saw, and it makes for these cathedral-like spaces. It's absolutely gorgeous. So we were convinced that we could then go on and do even more things with this. This is the opening ceremony. So it was kind of, in fact, it was rather like a musical instrument rather than the musical instruments being on the outside. We did some benchmarking on this. These are all of that's the entire pavilion being transported. So that's the flat pack element. Then we're trying to find out how structurally we're able to compare with simple post and beam and wooden frame, stud frame structures. So we need to do that homework as well. That's in progress at the moment. But then, of course, this commission came for the subject of today's talk. So I'm just going to go to that very, very quickly. This is the Grand Palais Éphémère. This is where the Forum Bois Construction, one of the biggest meetups of the timber industry in Europe, happens. This will be happening this summer. And this is where we were asked to do the temporary amphitheatre, which is sort of like the heart and soul. This is where all of the exchanges are made. And all the speakers do their talks. And this is where, that was basically the rectangle that we were given. We had a look at how we could basically provide a structure which would give us the acoustic comfort and the protection from all of the what's going on around, the noise of the fair going on around. And we came up with the conception of this rectangle using a series of curved panels. The next question was, how big should the curved panels be and how will they stand up? Because we're obviously not going to be using the banana stem configuration. We have to find something else. When we look at the panels all standing up to make the rectangle, that's what it starts to look like. It's rather like a curtain in wood, but this is 6 centimeter CLT. How do we get all of that to stand up? Well, then we go back to our engineers, NEI, the engineers, Belgian engineers. They're a wonderful, wonderful firm, extremely good with timber. How do we get all this to stand up? Well, we went back to nature again. This is how the panels would perform if you just sort of hold them on the ground and then let them go. So this is all the pre-engineering work that we're looking at in order to calculate what to do. We looked at another system which you find in nature, which is bird bones. Very, very light, very, 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 very strong. Not the concentric circle model that we saw a bit earlier, which is more of the human bone thing, which is made to carry weight. Bird bones, when we looked at them more closer, we found a whole bunch of different structural approaches, and we started to apply those. This is our first test using metal rods in order to hold the panels in place. These are 5.25 meters high. This is all in locally sourced Douglas fir from Piso. That's what the inside of a bird bone looks like. And this is how we're starting to combine all of the elements of curved CLT panels in order to get them to work as structural columns in sets of 3. So when we stand them up, that's how they look. They can resist the wind loads, they can reduce any impacts that they may be subjected to during the course of the fair. That's looking at sort of a down section, looking at what they at how they're all put together. And this is basically what the amphitheatre is going to look like if you are able to come, and let's hope that everybody's able to be mobile again this summer. This is what it'll look like in the Grand Palais Éphémère this summer once it's constructed. So all of these elements are now being assembled right now in the workshops, and they'll be transported to site. They'll be bent on site and then pinned together on site. What's going to become of this temporary pavilion? Because once again, we're building to disassemble. Well, it's going to be shipped off and it's going to be used right now. It's being studied as a food hall. It's going to become a food hall somewhere on the outskirts of Rennes, let's hope. But again, there are more barriers to do with all of this than just simply engineering. There are also questions of insurance companies who say, well, I don't want used elements. And I think that as we start to develop more and more approaches which integrate circular economy principles, the more we're going to have to deal with another set of barriers. We've dealt with the termites, with the fire, with the seismic things. Now we're going to have to deal with a whole bunch of other elements, which is, can we reuse all of these elements in a structural way and satisfy our clients who are taking on something which has already had a previous life, but we're absolutely committed to going all the way with that. I'm just going to, if you can launch the, that's an animation there. If somebody can click on that to go, yeah, there we go. So this has become, I mean, this Musa project, this research project, which you've now seen some of the flowers that have come out of it, has really become for the office almost an existential idea. Where should we be going with constructing? Should we be building things? Or should we be completely rethinking about the way in which we inhabit the planet? Should we be aspiring to leave the ground, to build high, not to reach the skies, but to release the ground to other species who need to be on the ground? Should we be living in structures which offer us more than just a view to the exterior? And should we be borrowing more materials from nature and geological cycles and fusing them for our own purposes and then releasing them back to nature? How do we do that? And can we imagine streamlined manufacturing flows using cold processes, which is what nature uses as well, or body temperature at the very most, just as our cells manufacture molecules which build the building blocks of life themselves. So this is where we're going with the Musa project, and perhaps one day we'll be able to do much more ambitious things with this technique. And that's the end of my presentation. Thank you very much for your patience.